Okay, so let me start with an apology to the many viewers who are waiting for my new releases. I have promised in my previous videos that I will continue to make more tutorial videos on Olex2. And believe me, I was actively trying to find a good topic to make the video. However, since there are tons of great tutorial videos already online, especially the series from the development team of Olex2, so it is very difficult for me to find a good topic which I will not repeat myself or others. I'm probably a little bit too ambitious because I want to make high quality videos. I want to make sure my videos will stand over time. Now I kind of want to relax a little bit and make it less intense. You can probably enjoy it as a popcorn movie. I will make sure to put the link to the Olex2 tutorial I mentioned just now down below. So these days I finally got an idea on the topics. That is what I'm going to talk about today. So my idea is many new beginners are exposed to large amount of tutorials and these trainings are necessary. However, after that stage, they will need some more real-life practices. Taking traditional Chinese Kung Fu as an example, you can spend many years training with your master and learn all kinds of skills and tricks. But if you have never ended up in a real fight, even a fight on a stage, then you can never claim you have mastered the skill. Same rules apply to any learning process. Here you have learned all kinds of skills, tricks, but once you are challenged by a real dataset, you literally get lost right away. You don't know where to start. So from today on, I'm planning to start a series of case studies. I'm going to find some random dataset from CCDC and reproduce their refinement. A side note, starting from June 2011, RUCI journals began to require that zip files should contain the structure factor. So any zip files older than that would not have structure factor embedded, and you would not be able to refine them. So without further ado, let's start. As shown on screen, here's a real dataset I downloaded. And when you download the CCDC data, make sure you choose the whole data package, meaning the safe including the check safe and HKL file. And this is a deposit number if you need to download the data yourself to practice with. So first, you can see that this package actually has three files: the safe file, the check safe report, and the third is HKL file. Actually, normally you should only have two: one check safe and one safe file, which including everything like the refinement details and HKL embedded. However, in this case, most likely the safe was not prepared properly, so the author has to provide the HKL file separately. Okay, anyway, let's open the zip file with Olex2 first. So open with Olex2, and immediately you can notice here the top link shown as green. I remember it should be blue most of the time. The reason is, see here, it's zip file. So if you want to refine, you need a res file here, and then you can refine. Okay, let's first take a quick look at the general result. First look at here. Most of them are green, and this is a light green. Not ideal, not perfect, but not too bad either. But here, this is highlighted in red, so something is wrong. And other than that, the rest numerical indicators looks fine. And if you click on this percentage icon, Let's take a look at this F observe over F calculation. It looks generally in line. It's a fairly straight line, okay? So overall, this data set should be fine. And but let's take a look at the structure. Immediately, you notice that the oxygen here is a isolated oxygen atom without a proton. This is not necessarily considered wrong because sometimes it's difficult to add hydrogen to the free oxygen solvent, actually water, I should say. But here, it is clearly a mistake, or it's not treated correctly. So the three oxygens are bonded together, which is definitely not right. So I suppose if you hover the mouse over the atom, you will see the occupancy is not 1. So this one is at 0.4. How much is this? 0.25, 0.2. So they add up to be 0.85. So apparently they also want to treat this as a disorder. However, the way they treat them is wrong. They should not put them all in part 0. Instead, they should assign a different part number to these individual atoms. For example, you can put this one as part 1, part 2, part 3, etc. Okay, let's continue to examine the rest of the structure. And this ellipsoid looks in good shape. They are not terribly elongated in certain direction, or not huge either. And this hydrogen bonding are reasonable. So generally this part looks fine. And if you look, let's see here, there is a disorder here. Okay, the next one you want to see is just press Ctrl M to bring up the map. And this is a difference map, and you want to see there's no big positive or negative electron cloud. And they are mainly in the heavy metals, so this is also fine. Okay, now let's check the check-safe report to see they have provided any hints to the overall quality. Okay, we have a short intermolecular donor acceptor contact oxygen 4 and oxygen 4W. Let's see where is oxygen 4 and oxygen 4W. So you just type Selects oxygen 4, oxygen 4W, enter. Okay, so these two are shown. Okay, so this is reasonable. As I mentioned, you also should not model this cloud as 3 discrete oxygen, and they should not use part 0 for them. Okay, so this is reasonable. We can take care of that later. What's the next? So the formula string are different. Let's take a look. Yeah, it's 3 water here, 0.6. Yeah, here they calculated only found the liquid oxygen, but not the hydrogen assigned. So the calculated did not find the hydrogen, but the reported formula they also included oxygen. Well, I'm not 100% sure what's the correct way to do it. If it were me, I probably will add an explanation here saying that due to the data quality or due to the X-ray diffraction, hydrogen was not found, but it should be there based on the chemistry knowledge. Okay. Then, yeah, the molecular weight differ is related to the first one, and the third alert is similar to the first one. Let's see. Okay, so generally it looks not too bad. Okay, let's come back to the refinement, see if we can reproduce it. So first step, before we start from the very beginning to do the solve, we want to make sure we can, this data was not altered in any way. So we just click refine. See how the Olex2 will show the result. Okay. All of a sudden we have a big shift. I don't know which one is it. See. Okay, so we actually have several of the red highlighted area. First, the shift is outrageous. So this hydrogen is apparently does not settle down. So something is wrong here. Let's see if we press Ctrl M to bring up the map. Again, there's no electron density negative or positive here, so we cannot tell. But we'll see later. We will try to reproduce the whole process and see if we can end up with the exact same structure, and if we see that same alert again. So the second good feeling is 1.4. Apparently there's something else wrong, and negative occupancy for atom H10C. Let's find that one first. Select H10C. Where is it? Okay, let's just turn off the map first. Okay, now it is. So we can see this is a disordered part, and the oxygen is negative occupancy. If you want to know more, we just type info. And now we can see, this is a chemical occupancy is negative, so it should not be there. And now we bring up the map again. Let's see is anything outrageous. Surprisingly, it's not. But let's see, this is negative. How about the carbon? Okay, the carbon is 0.25 occupancy, but this is negative. So let's see, click here, click this atom icon to see how they find this hydrogen. Okay, so apparently they did not using the writing model, and they try to refine it freely. Okay, if the data quality is good enough, and if you have electron density to has Q peaks in this position, then this is okay. But I don't think this data quality is that good. Let's see if I remove this proton and refine again. Do I see electron density there? Control, there's no Q peaks. Okay, Q peak is 5. Apparently it's much little. Let's just change it to maybe 20. Refine again. Okay, I don't see any electron density there. And I don't see any density there. And this bond is 1.2. And let's click here. Yeah, again, it's not running as a mod. It's not refined as a running model. It's just refined freely. Because of the data quality, you don't have discrete electron density, or in other words, Q peak in that region. So this cannot refine. This refinement cannot settle down. So if I just show part 0 and 1, this is part 1, and part 1 looks fine, and this is 0.7. Yeah, this is not right. See, you have to tie the occupancy of the hydrogen to the carbon is bonded, so the occupancy has to be the same. So you cannot say I have 70% of the carbon here, but only have 50% of the hydrogen here. Where's the difference, right? This is have 79. Yeah, so this is the wrong way to treat this. Let's show part 0, 2. And apparently I deleted the other one, but you can see the original one still left here. The angle is definitely wrong. This is doesn't look like a tetrahedral configuration. Let's see the angle, okay? 1, 2, 3. And hover your mouse over here, you will see it's 127. It is definitely wrong, right? The tetrahedral angle should be 109.5 something, right? So, and this bond is outrageous. It's 1.2 something. It's definitely much too longer. And if you see the occupancy, this is 0.29. This is 0.68. Again, they are not tied. So this is the wrong way. Plus, if you notice, here the occupancy is free, which is not correct. The disorders, if you really think this is disorder, then you should tie the two. Let's see, show the both part by typing show P, and you will see these two occupancies should end up together to be 100%. You cannot just refine them freely, like this is 29, this is 70. Actually, they naturally end up to be close to 100%. That means they are indeed disorders, but you should mathematically tie the occupancy of them to be 100%. Similarly, you should tie the occupancy of the bonding hydrogen to their master carbon. Okay, so this is certainly wrong. Chemistry doesn't make chemistry sense. Okay, so this drive to a point I want to mention in the very beginning. So even the numerical indicators shown here are generally fine. The structure model is wrong because you cannot have over 1.2 angstrom of CH bond. So I want to stress that most beginners tend to rely too heavily on these numerical indicators. For example, they only look at the I1 value sometimes, or other few indicators like WR2. This is not the full story. The correct way is to look at all the full picture altogether. It has to make chemical sense first. George Sheldrick once said, famously, and I quote here, "With enough restraints and constraints, you can pretty much fit an elephant into any data." But apparently not all data are from an elephant crystal, right? If such crystal exists at all. So what I'm trying to say is, don't look at only these numeric indicators. You want to make sure it has to make a chemical sense. For example, if you start with a periodic ring, it just cannot turn into a benzene ring magically, okay? Has to make chemistry sense first. Okay, now I'm going to start from the very beginning and start from scratch to show you how to reproduce the refinement. Okay, so first go here, solve, click solve, choose shell XT and intrinsic phasing. Let's click solve, click yes. Okay, surprisingly, it takes quite a few seconds. I think it's because I'm using some of the computer resources is recording this session. So, but anyway, let's come back to the topic, and let's just remove the text here. Lines, let me say 15 maybe. Oh, it's 15. It's already there. 10. Okay, so now apparently, I want to show you from the very beginning how I will treat this data set if it's mine, okay? And first you want to turn off the difference electricity map by pressing Ctrl M, and then you see this isotropic model, and immediately if you see this free flowing nitrogens, it must be oxygen because it cannot be NH2 or NH3, so it has to be H2O. So what you're going to do is select this either by clicking oxygen, or you can select and type name O. That will also label it as oxygen. Okay, and here looks like a methanol molecule, but so here's what you need to get information from the sample owner. You need to ask them, did you use methanol to grow your crystal? And in this case, I guess no, because the previous the data I downloaded did not show a methanol molecule here, so I suppose they only use water somehow. So here something is wrong, so for now you just delete it. Don't worry, it will come back if it's real. Okay, so just delete it, and let's continue to look the whole structure here. And if I memorize correctly, they have nitrogen here, and if the data quality is high enough, the program can tell the difference between carbon and nitrogen. But if the data quality is not very good, then it will not be able to tell them apart. But for now, let's see how the data is. The data looks like to fairly high resolution, so we just leave it for now. Let's see if the program can pick up or show us something indication here. Okay, and what else? So oxygen, yeah. Okay, let's just press Ctrl R. Let's have a brief refinement. Let's come here. Yeah, 4 cycle is fine. We'll leave this unchecked for now. And good. See here, it has Q peaks right next to the atom, indicating this atom should be heavier. So what I'm going to do is just change it to nitrogen. Okay, and bear in mind that this 12.11, what's the shift? Yeah, this thing. So here, so that shifts a lot. So there's something wrong with it for now. We don't know yet. Okay, so let's refine another round. Okay, so the I1 decreased. That means we did something correct. And here the Q peaks are gone. Okay. Let's see. Let's try to, refine another round until this shift stabilize. Okay, good. And let's the maximum peak is here. Yeah, that got to be oxygen. Let's just name it oxygen for now because it's discrete. It's not bonded to anything, so it has to be water. Okay, for now, just name it water, and recall the model we see in the very beginning. This is a 3 oxygen that also has modeled, which is clearly wrong. You should not model that, but we'll leave it for now. We'll take care of that later. Okay, what's the shift here? If you click here, okay, that's oxygen. Okay, that's fine. For now, I think it's better to keep our focus on the main part. Let's just delete this one. And refine to the shift stabilize. Okay, which is not too bad now. Okay, now I think it's time to turn this isotropic model to anisotropic by typing anis, or you can, click here. So just enter and press Ctrl R again. So that I1 dropped from 12.03 dramatically to 7.71. That's pretty good. Refine again to see if the shifts will settle down. Yes, it's going in the right direction. What's this? Yeah, so this, if you can recognize, this is a disorder that also has attempted to model, but the model the wrong way. Okay, if you see here, clearly this ellipsoid is stretched, perpendicular to this plane. So we are going to model that too, but I will show you what's the correct way to model it. And also you can see this is also disordered. Okay, so there are two carbon atoms are disordered here, and other than that, it's good. Let's see, refine again. Yeah, like I said, the Olex2 have many ways to enforce one action. You can click, or you can type a command. Either way is fine. Okay, so the shift is stabilized. Now let's model this disorder for now. Okay, so the way is to just Control Q to hide this Q peak first. That way we can easily select this carbon. Then just either you do a model split, or you can just type split. Okay, now, so this one, the anisotropic atoms was replaced by two isotropic atoms, and each of them are assigned a part number and starting occupancies 50-50. They will refine to the real number. Okay, so this is part 1, part 2. This is also part 1, part 2. Okay, without changing anything, we just refine it to see how it will settle down. We can always adjust it accordingly. Okay, so after refine 2 runs, and now you already can see the problem. See that? Part 1 with 1 big ball, 1 small ball. Part 2 with 1 big ball and 1 small ball. There is a Hirschfeld test, which doesn't apply exactly here, but you get the same idea here. So basically the bond, so the atom directly connected by a bond should have a similar U along the bond.